So, last lecture we are discussing about the work index, and I said that in this lecture I will show you, that is how we can use this useful information, that is your work index of a particular material. So, that is why I have given this question, that is probably which is coming to your mind also, that what exactly is a work index and how can I make use of it. I would say that work index is to measuring energy in size reduction. It is similar to what we use a meter to measure distance. That means, it is a almost equivalent to your unit. That means, your work index is the very essential thing we must know to calculate the energy consumption into a comminution process. It is a standard measure that brings all size reduction circuits onto a common basis for comparison. That means, if I perform the test based on the guideline given, that is, we should not alter the machine, we should have a bond mill, it may be a rod mill, it may be a bond grinding mill, and we should do the test properly. Then what will happen, if we have your different equipment and we want to have a particular feed material to be fragmented into a particular product size distribution, we can calculate for comparison purposes, that is, which circuit or which machine has consumed the least energy. Now, let me recapitulate that for giving the example, that it is the bond work index, the equation is, that is when we basically the work input, that is we can write W is equal to 10 W I 1 by root P 80 minus 1 by root F 80. There we have used, that is your here the W is the work or the energy input per ton of material. That means, if I know the P 80 and F 80 and the work index, we can calculate through this equation that what is the how much is the work input required per ton of material, or it has consumed per ton of material. How do I do it? So, for that what I have to do? I have to collect the feed material from a circuit. Suppose there is a crusher. So, whatever the material going into the crusher as feed, I need to take a representative sample from there, and I must need to do the size analysis of that. Based on that size analysis, I should get the value of F 80. Similarly, whatever is getting discharged from that crusher, I should take a representative sample from that crusher product and do the size analysis to estimate the value of P 80. And before that, that ore material, that is material which is being fed, I should do the work index calculation if the value is not known. If it is a common mineral, we should get the W I value from a standard source or from a standard textbook even. Now, let me give an example, that is how we can use this work index. Suppose a grinding circuit is processing 450 tons per hour of dry feed with a mill, that means a grinding mill. Do not worry about that what mill and all this, we will discuss in due course of time. It is a particle breakage device. With the mill drawing 3150 kilowatt at the pinion, pinion means at the where it is getting basically say getting hooked up, that is called the pinion, where it rotates. So, while processing a 450 tons per hour of dry feed in a mill which draws 3150 kilowatt of energy or the power, the circuit feed is 80% passing 2500 micron or micrometer, and the circuit product is 80% passing 212 micrometer. Now, with that what we can do? Now, we can calculate the work input is therefore, that is the input energy is 3150 and we are processing 450 tons per hour. So, that is 7 kilowatt hour per ton. So, that is the work. So, per ton of material to be ground to that particular size from a particular feet size, it is consuming 7 kilowatt of power. Now, there is a term called WIO, which stands for operating work index. So, the operating work index for this circuit is calculated as follows, that is the W, and let us say that your WI I do not know. So, what is that operating work index? That means, when the particle is getting broken, what is that work index of that particle during breakage, or say actually what is that operating work index. So, we can put this value, that is in place of W, that is equal to 7 kilowatt hour per ton is equal to WIO. Instead of WI we are writing the WIO, because it is the operating work index. It may not, because your no mineral is a pure mineral. So, it will have some kind of your impurities. So, we want to know what is the operating work index. So, that is the WIO into 10 by square root of 212, that is coming from your P80 size, and that is the F80 size is 2500 micrometer. So, solving we are getting WIO is equal to 14.4 kilowatt hour per ton. That is the operating work index for that material, which is being crushed or ground from a 2500 micrometer to 212 micrometer size or 80% passing size. We can now estimate the needed W if, for example, we accept a grind P80 of 250 micrometer. This is very interesting. Say here we are saying that we are getting a circuit P80, that is your product 80% passing size is 212 micrometer. But if your metallurgist says, when you are having a discussion as a mineral processor with a metallurgist, we say that can you accept a little bit of coarser grind, or maybe your mineral processing engineer who is looking after the downstream processes, you are the in charge of the size reduction processes and your colleague is in charge of your downstream processing circuit. So, you say that we are consuming a lot of energy in my milling circuit, that is your grinding circuit. So, if I increase this 80% passing size to 250 micrometer, first let me discuss with my processing colleague that to show that how much of energy we essentially will be saving. So, if we accept a grind P80 of 250 micrometer, then what will happen? So, W is equal to 14.4, where from 14.4 you have got it from WIO value. So, that is the WI value. So, that is 14.4 multiplied by 10 by root 250 minus 10 by root over 2500 is equal to 6.2 kilowatt hour per ton. So, you see that when we are breaking the rock to 212 micron, it was consuming 7 kilowatt hour for per ton of material to be broken. If we accept, if your processing friend who is in charge of your downstream processing, if you can convince him that okay, or if he agrees that okay, I would mind if I get 250 micrometer, then you see that your energy requirement will be your 6.2 kilowatt hour per ton from 7 kilowatt hour per ton. Or maybe this information you can use it to say that okay, we will have the fixed energy consumption, but can we increase the capacity of my mill? Yes. So, with the same mill power, we can increase the tonnage to 3150, that means it was consuming 3150 kilowatt divided by 6.2. So, that means your capacity will be increased to 508 tons per hour from 450 tons per hour. So, these type of calculations we can do it, as in the very first class we said that mineral processing operations are basically a compromise between the your say how much of money is required to get a desired your separation. So, it is not the your say perfect separation we look for between a balance between your economic constraint and your product quality constraint. So, this example shows that if we with this WI concept, that is the work index concept, we can do all these permutation and combinations, that is keeping the energy consumption fixed, we can increase the your say the capacity of my mill by more than 10% by increasing a little bit of your product size distribution from 212 micrometer to 250 micrometer. Estimating the new production rate by changing one of the variables is just one of the ways you can use this equation. It is one of the applications. So, if we make the feed size very large, now let me explain you that what exactly this Wi, when we said that it is coming from a very infinite size to below your 100 micrometer size. See that if we have this 10 by root f80, if your feed size is very large, so what will happen? That it would approach a value of 0, because your f80 could be very large in relation to 10. So, it is 0.00000 like that. So, it would approach a value of 0. If at the same time we make the P80 equal to 100 micrometer, so what will happen? Sorry, this is not U, this is the micron. So, the term 10 by root P80 would be equal to 1, and W, that is the work input, would equal the work index. So, what I try to say that here, say suppose this value is very high. So, then what will happen? This 10 by this value will become almost 0, and if this is 100 microns. So, 10 by 10 it will become 1. So, this will nothing but your work input is equal to your work index. So, that is the Wi. So, that is why the work index of this circuit is the equivalent amount of energy it would use to reduce this ore from a very large size to a P80 of 100 micrometer. Hope now this is clear that what did I want to mean, that is when I said that Wi stands for bond work index, which is basically that how much of work you require to break a particle from an infinite size to below 100 micrometer. Now, for any circuit, whether a crushing circuit, a rod mill circuit, which we will discuss in due course of time, or a closed ball mill circuit, the work index always means the equivalent amount of energy to reduce 1 ton of the ore from a very large size to 100 micrometer. So, that means it is independent of the machine, or you can say that work index is basically telling that in any machine from an infinite amount of size, infinite size to a size of 100 micrometer, and if you want to process 1 ton of material from that size to this size, then it will remain constant. So, that is the equivalent amount of energy irrespective of that. So, that is why I repeat it again, just as the meter is used to measure and compare distances, the work index thus measures and compares energy uses of size reduction processes. Now, if I ask you to calculate the work index efficiency, I will define it. What is work index efficiency of your grinding circuit? Work index efficiency is defined as the ratio between the test work index, that is represented as now WIT, to distinguish it between the two work indexes we are discussing, and the operating work index. That means, in the laboratory in a controlled environment, when you have done the test, that is the test prescribed by Mr. Bond, what is the WI you got, and while operating the machine for a particular size reduction or say particular specified size reduction, what is the operating work index you got. So, it is the ratio between the two. So, for any given circuit, when WIO, that is your operating work index, is less than the your test work index. So, that means the circuit is more efficient than that average, and when WIO is greater than WIT, it is less efficient. That means, in a standard condition, if I break a particular rock from a particular specified size to another particular product size, how much of energy essentially it would consume. So, that is the laboratory test. Now, you have got a different circuit, you have got a different feeding arrangement, you have got different types of your say breakage mechanisms, which we have briefly discussed in the previous lectures. Now, what is the operating work index? So, if the operating work index is less than the test work index, so that means your process is very efficient, and if it is vice versa, so that means it is less efficient. Let us see that. Now, for the previous case, that is the numbers where I have given, we have calculated that operating index was calculated to be 14.4 kilowatt hour per ton. Now, if we have performed the bond mill test, suppose that you have performed the ball mill test prescribed by the bond, and you have got a value of work index of 15.8 kilowatt hour per ton for that particular material. So, in this case, your work index efficiency is 15.8, that is the work index WIT divided by WIO, that is 14.4. So, it is 1.1 or it is 110%. So, that means, your circuit is 10% more efficient than the average circuit upon which the bond design method is best, because the bond mill, that test work index is proposed, because there is no theory in that, that is also an experiment. So, you have got a circuit that you will feed this material like this, you will have this type of configuration of your say your balls, that you will make it you will try to break your particles from a particular feed size to a product size of less than 100 micrometer, and that is an ideal test condition. So, you have got a machine, you have got a circuit, and you are saying that my circuit is 10% more efficient than the average circuit upon which the bond design method is best. By calculating your circuit's work index efficiency, you can compare it to the bond average of 100%. That means, the bond average you can assume that this is equivalent to 100%. So, now the same material suppose is broken into 4 parallel circuits. So, each circuit the operating efficiency work index efficiency you can calculate based on the how many tons of material you are processing per unit per hour, and then how much of energy is being consumed. Based on that you can calculate what is the operating work index for all the 4 parallel circuits, and you can compare it the work index efficiency, and then you may say that okay, the circuit 3 is the most efficient and maybe your circuit 4 is the least efficient. Then as a plant engineer you should take some kind of your corrective measures, that is what is going wrong into my circuit 4 and then how do I improve the energy efficiency of that circuit. Okay. So, in literature in a website we have seen this amazing your say actually this sentence which I liked it. So, that is why I could not prevent myself in say telling you this sentence, that thanks to the amazing standardization of size reduction that the concept of work index provides, you can also compare it to the efficiency of other circuits both similar and dissimilar. That means, I can have your plant auditing, like I can have the your circuit your energy estimations, and even the most efficient circuit we can do the your say detail analysis, like we can do post-mortem and we can find out that why this circuit is most efficient, and then why can't we implement or say reproduce this circuit into the another parallel circuits. So, that my overall energy consumption is less. And you can also monitor efficiency, increases as you work through a grinding circuit efficiency improvement program. Even based on this logic, you can have some on stream your analyzer, which will give you the basically the work index efficiency or say operating efficiency of your circuit, and then you can pinpoint that which circuit I should act to modify it. So, for this lecture actually I have consulted these 2 literature. One is by Fred Bond, that is the crushing and grinding calculations. It was published, it has got the 2 parts, part 1 and part 2. It was published in British Chemical Engineering Journal June 1961, and there is a basically if you Google it, that Metcom Tech grinding bulletin, you can get all this interesting your feature related to these work indices. So, if I summarize it, the comminution fundamentals, that we should know that why what is the fundamental difference between your blasting and comminution. Comminution we want a progressive size reduction, not and a blasting you are having a size reduction in one go. So, you do not have much control on the product size distribution, but as a mineral processing engineer or as a comminution engineer, you should know that how do I control the sizes at each stages, so that I do not generate much of finer product than what is required. So, it is a progressive breakage of particles, and for that we must know why the particles are broken, what are the characteristics of that your ore which actually say promotes the process of size reduction or which inhibits the process of size reduction, what are the parameters, and then what are the various ways we can break a particle, that also we should know, and then what are the different machines which are available. So, that we will discuss in the next say successive lectures, but how much of energy is being consumed, that means energy consumption is a very vital parameter for your size reduction processes. So, what is the concept of WI, that is the work index, and then we have also discussed, we have through examples, that is how do we use this WI value for calculating the your capacity of a plant, and if we manipulate the product size distribution, can we increase the capacity of my plant by manipulating a little bit of your coarser product size. And we have also discussed through examples, we have shown that how we can compare the performances of different comminution circuits through this unique parameter called Wi. So, that is the work index, and we have also discussed about the operating work index efficiency and your the laboratory work index, that is called the bond work index. So, next class we will start with the different machines. So, till then, thank you very much.